بسم الله الحمد لله والصلاة والسلام على رسول الله. الطلبة الأعزاء، السلام عليكم ورحمة الله وبركاته، وأهلا ومرحبا بكم في هذا المحور السادس من مادة Engineering Drawing 2 والذي بعنوان Basics of Assembly Drawing. Topics of this chapter are the following. We will start by introduction. Next, we will present detailed drawing, and finally, we will present assembly drawing practices. First part, introduction. Working drawing is a set of drawing used during the work of making a product. Working drawing details contain detailed drawing and assembly drawing. Detailed drawing is a multi-view representation of single part with dimensions and notes. Then assembly drawing is a drawing of various parts of machine or structure assembled in their relative working positions. The purpose is the following. Detailed drawing conveys the information and instruction for manufacturing the part. Assembly drawing conveys, first, completed shape of the product. Next, overall dimensions. Third, relative position of each part. Fourth, functional relationship among various components. بسم الله الحمد لله والصلاة والسلام على رسول الله. الطلبة الأعزاء، السلام عليكم ورحمة الله وبركاته، وأهلا ومرحبا بكم في هذا المحور السادس من مادة Engineering Drawing 2 والذي بعنوان Basics of Assembly Drawing. Topics of this chapter are the following. We will start by introduction. Next, we will present detailed drawing, and finally, we will present assembly drawing practices. First part, introduction. Working drawing is a set of drawing used during the work of making a product. Working drawing details contain detailed drawing and assembly drawing. Detailed drawing is a multi-view representation of single part with dimensions and notes. Then assembly drawing is a drawing of various parts of machine or structure assembled in their relative working positions. The purpose is the following. Detailed drawing conveys the information and instruction for manufacturing the part. Assembly drawing conveys, first, completed shape of the product. Next, overall dimensions. Third, relative position of each part. Fourth, functional relationship among various components. بسم الله الحمد لله والصلاة والسلام على رسول الله. الطلبة الأعزاء، السلام عليكم ورحمة الله وبركاته، وأهلا ومرحبا بكم في هذا الجزء الثالث من المحور السادس من مادة رسم هندسي 2 والذي بعنوان Assembly Drawing. Three types of assembly drawing we will explain now. First one is called exploded assembly drawing. The parts are separately displayed, but they are aligned according to their assembly positions and sequences. Second, general assembly drawings. All parts in this drawing are drawn in their working position. Third type, detailed assembly drawing. All parts are drawn in their working position with the completed dimensions. Here we have, for exploded assembly, one example. Here it is as exploded assembly for all parts to show all parts exploded, and here we have the finished product. Another example for exploded assembly here. All parts are here, not assembled, but exploded and ready for to be assembled. General assembly. Here we have the pictorial view for assembly, and here we have orthographic drawing for assembly. Here it is 3D, here it is 2D. Another example for assembly. This machine, for example, only dimensions related to machine's operation are given. Here, different dimensions for the whole machine. Here also, only dimensions related to machine's operation are given in tabulated form. Not shown, but it will be given in tabulated form. We have another example here for general assembly. No detail, but general details for part name and numbers, quantity of parts here, and how to be assembled in two views. Here we have detailed assembly, working drawing assembly. All details or majority of details for all parts with assembly are shown here. Required information in general assembly drawing. All parts drawn in their operation position, part list or bill of materials, BOM, item number, descriptive name, material, quantity required per unit of machine. Third point, we have leader lines with balloons around part numbers. Finally, machining and assembly operations and critical dimensions related to operation of the machine. These are the required information in general assembly drawing. Placing of information used in this course. Here we have assembled part and reference numbers. General note down. Here we have the title block, the part list. Part list bill of materials used in this course. Locate above or beside the title block. Fill the table from the bottom. Use this template. Here we have number 1, 2, 3, 4, the number reference number of parts, part name, required number, and material or notes. For example, supports, we have, it is number 1, reference number 1 on the graph, and here we use 2 parts as a support. The material is cast iron. Reference number 2, it is shaft, but we use only 1 as a quantity. Material it is stainless steel. Reference number 3, it is set screw. Number and the quantity, it is 1, and material, it is stainless steel. Here we have an example for another allowable place for bill of materials. This is the another allowable place for BOM, bill of material. It is up and in the up region for the graph or sheet paper. We have here the reference number. Here the reference number of the part used, description and title here, and number required or quantity, and here it is some required notes. One example here for number 15, for example, it is a spring. Number 15, it is here. This is spring. Okay. This is part number 15. Number used, quantity is 1. Steps to create assembly drawing. First, analyze geometry and dimensions for all parts in order to understand the assembly steps and overall shape of device or machines. Second, select an appropriate view. Third, choose major parts. That means parts that have several parts assembled on. Finally, draw a view major parts according to a selected viewing. This is point number 4. Point number 5, add detailed view of the remaining parts at their working position. 6, apply section technique where relative positions between adjacent parts and needed to clarify. Number 7, add balloons, notes, and dimensions, if any. Number 8, create bill of materials. Some general practices. The number of views can be 1, 2, 3, or more as needed, but it should be minimum. Also, a good viewing direction is that represents all or most of the parts assembled in their working position. We'll take an example now. Selection of necessary views. We have part A with 2 views and part B to be assembled. Student A can make assembly drawing like that, and student B can make assembly drawing like this, which is an appropriate view for assembly drawing. Definitely, that one. General practice. Hidden lines usually omit unless they are absolutely necessary to illustrate some important features that the reader might otherwise miss. One example here, hidden line, omit or not. Part A at part B to be assembled. It can be assembled with this manner, like this, or like this. So point number A, it is good because these hidden lines give us information about this hole. Point B or drawing B, it is poor because no information about hidden lines. Point C2, it is poor, it's not good. So the best one to use this representation, and here hidden line give us information about some shapes and features for this part A. Another example here for part A and part B. First example with A to be assembled like that, and B to be assembled like that. Which is better? So A, it is better. B, it is poor. Section technique is usually needed to clarify matching of the parts. Part A and part B, the same example. So like that, it is correct, okay. That one, it's better. Use different section line styles for adjacent parts. We have to change inclination here for section lines. If we want to remove colors here, so this representation it's better with section. Do not draw section lines on sectional view of standard parts. For example, threaded fastener, washer, longitudinal cut of solid shaft, pin or key. We'll take example here. We have to make assembly of these 3 parts. So part number 3, it is a standard part. Okay, if we make assembly with this pin, okay, now with section, first possibility, second possibility. So do not make etching and section lines on standard parts. Okay, this one is good, this is poor or wrong as per standards of drawing. Here another example. Okay, the tapper pin, it is a standard part. This also shaft for this assembly. If we make assembly, this shaft here and the support and the tapper pin, okay, right. Now if we use section, first possibility, second possibility, third and fourth possibility, which is good. Okay, so A, it is poor, not good. B, 2, it is poor. C, it is poor also, but better than A and B. So D, it is the best one. Okay, if we make off the colors, we'll see here. So do not make etching for standard parts here and for the shaft. This one, it is good. This one not. Here we have another example for assembly steps. To make assembly of these three parts, we will start by part 1 and 2. Okay, and finally make assembly for the third part. Here we have three possibilities. Okay, which is better? Let's check. A, it is poor. Okay, B, it is good. So the pin, it is a standard part, but here we have section, a cross section, not longitudinal section. Okay, so B, it is good, and C, it is good also, but it is better to show details here. If we make off colors, okay, it is better here. Leader line practices. Drawn from the inside of the part to the balloon and placed a fillet circle at the beginning of the line. Here the balloon to indicate the number of this part. Okay, starting from the part. Drawn in oblique direction. Okay, this is for part 2. Here we have an example for making assembly. First part, second part, it is the shaft, housing, cover plate, bearing, cap, screw. To make assembly, we'll start to make assembly shaft with bearing. After that, place these sub-assembly together and make the bearing in its placement. After that, place the cover and finally tighten the screws. Okay? And finish to delete and to remove some lines here and here, here also, okay? Now it is good. Interpreting assembly drawing. To make assembly steps, to analyze function of each part in machine, and to make a design, to understand the design concept. Here we have this assembly. Assembly steps are the following. Install bearing to the shaft, install the bearing shaft unit to the housing, install the cover plate, and tighten the screw. Function of main parts. Bearing. The function of the bearing is to support the rotating shaft, and the function of the cover is to control an axle movement and to prevent the bearing unit from rotation. As a design concept, to avoid direct contact between rotating shaft and housing, as well as cover plate by using a bearing and clearance holes. Example 2, leakage prevention unit. The assembly steps are the following. First, wrap a packing to the shaft. Next, install a stud to the casing. Install a stud to the casing here. Third, install the gland ring where its holes align the wheel stud. This one, install the gland, this gland as a cover, okay? And align it with the stud holes. Fourth, place the washer and tighten the nut. Last step. Function. First one, packing, preventing the leakage of a fluid inside the casing. So prevent the fluid to go outside from here. Here we have prevention of leakage. Second, gland, press the packing to make it radial expand and press the shaft surface. So the gland here, make a pressure here, and the pressure is transmitted on the shaft. As a design concept, to avoid direct contact between rotating shaft and casing as well as gland rings hole. Third example, fixing part on a shaft. As assemble steps, first, place the key on the key seats here. Second step, insert the parts to the shaft until their surfaces leans against the shoulder, here and here. Third step, insert color and then pin or rotate retaining ring into the groove. Here we have the retaining ring here. Okay, make it in its place, and here we have the pin and the color. So to prevent translation. As a function, the key, preventing rotational movement of parts, and pin and retaining ring to prevent axial movement or translation of parts on the shaft. As a design concept, retaining ring can resist lower axial force than collar pin unit. Next example, the assembly steps are the following. First, insert the part on the tapered end of the shaft. Insert the washer, non-standard. This is the washer. Third, tightening the nut and finish the assembly. Function, the washer, improve the distribution, the tightening force on the part. Improve the distribution and make uniform distribution of the tightening force. As a design concept, length of the tapered portion and depth of the tapered hole require a calculation. Here. Last example, parts having preloaded spring. We have spring in a free length, and here the assembly. Assembly steps. First one, insert the spring into the casing. Second, tighten the rod to the spring loader. Third, close the cap and tighten. As a function, spring plunger transmit a force from rod to spring. Second, keep the spring in a position. As a designer concept here, the spring plunger has a spherical surface contact to the cap. Therefore, the rod can align itself to original position.
Okay, think and analyze Tier 101, lecture number 4. So let's take a look at one of the examples in orthographic views, but before that, some fun. Are you available on Fridays or Saturdays for your AutoCAD workshop? If you are, wonderful. So we'll arrange for the workshops on one of the 2 days, or rather both days. So you are 12 batches. We'll divide those batches into 6 and 6. So 6 can go on Fridays and 6 can go on Saturdays. And then the next week, we'll have the AutoCAD lab. You know, Fridays. Monday, we have a bunch of lectures. Tuesday, bunch of lectures. Wednesday, Thursday, bunch of lectures. Come Friday and you're fried. Right? Well, Friday. Anyways, don't worry about that. Doesn't matter. Sense and nonsense, some more fun. Did you have your lunch yet? It's 2 o'clock. Okay, so the reason why I have posed this picture up is to make a point. We tend to spoon feed you. Yeah? Your academic appetite gets satiated over time, gets satisfied over time, and that's the reason why. That's one of the reasons why you tend to lose interest in academics in some time, maybe 1 semester, 2 semesters, 3 or 4 semesters, which is bad news. Bad north, east, west, south. Not good. The point that I'm making is you should never stop asking questions, no matter what. Academics or otherwise. Keep your curiosity alive and feed me with it. I'm hungry for your curiosity. Do not take me for granted. Question me, challenge me. I am bound to make a lot of mistakes. I keep making a lot of mistakes, so always question me, challenge me. I'll be very happy to answer your questions then and there. If not, then definitely in the next lecture. Okay, so this is pertaining to the question that I had posed in the previous lecture. So given the three orthographic views, is it possible for us to uniquely represent a solid, or vice versa? Can any solid be uniquely represented by three orthographic views? So this is a counter example. So let's say you have a block or a cube. You have a smaller cube on the back side, on the back face. You have again a smaller cube on the front face. Cube on this side, cube on that side, cube on top, cube on bottom. Okay, and then you have a void in there. So this is pretty much like, you have this cube placed dot at the center of the space, and all such cubes placed on the respective centers of the respective faces. Now for this solid, is it possible for you to represent this uniquely using orthographic views? Let's see. Hinge line separating the front view from the top view, and another vertical hinge line separating the front view from the right side view. Now if you sketch the views out, you will probably be getting something like this: front view, top view, and the right hand side view. Exactly the same story, exactly the same result. Okay. Now watch out for the conventions that I use. I use dash dot dot dash dot dot to represent the hinge lines. So this object is symmetric both along the vertical as well as along the horizontal. Okay, so I'm using dash dot dash dot, this convention, to represent the line of symmetry. Usually it's also used to represent the center line. So since these two are also symmetric about the horizontal and the vertical, I'm going to be using those lines. And of course, where are my projection lines? They have to be there. So the final lines are thick solid lines, whereas the construction lines are gray lines. Just for reference, it's always a nice idea to have projection lines, because otherwise things become very difficult to comprehend. Orthographic views uniquely represent a solid almost always, but not every time. For instance, in this case, it is not possible for you to represent the internal void here. Okay, so be careful about that. But almost always, these views, they work. Okay, orthographic projections. This is the fourth lecture, second week. Let's take an example. So we have to draw the orthographic views of the solid, dimensions of which are given. Okay, let's work it out one by one. So this could be a little boring, but if you follow the construction, step by step, things might be enlightening for you. The first step, preparing your sheet. Write your name, write your subject, what you're working on. Okay. Give all the details in the box over here. And this is the convention we use for the third angle orthographic view. So if you have a cone, the cone from this side is going to look like two concentric circles, and of course this would look like a trapezium. Mention this sign over here, or depict this sign over there. And actually, although this is at the center, or at the center of the sheet, it actually is on the bottom right corner of your sheet, right there. Okay, so once you have prepared your sheet, you're ready. Once again, mention the subject. More importantly, mention the scale. So we're using the scale 1:2. Okay. Now we are looking at the object along this direction. So this would be the front view of the object. that would be the top view, and the right hand side view would be from that side. Okay. Draw the hinge line, but before that just estimate based on the dimensions as to how your bounding boxes for the front view, the top view and the right hand side view are going to be placed. Okay. Once you make those preliminary measurements, start with the hinge lines first. So, this is the hinge line that separates the front view from the top view. Make the bounding box. Now, this is about 114 millimeters. This is about 32 here, and this is about 32 over there. 114 plus 32 plus 32, 114 plus 64, which would be something, some number, 178 I believe. That would be the length of this bounding box, and the height would be about this dimension, 45 plus 18. Okay. So, since I am using the scale 1:2, 178 over 2 would be 89. I am going to mention there, and that is going to be 31.5. Okay. 45 plus 18 divided by 2. So, the scale 1:2 would mean that 1 would actually represent the 2 scale, and this would represent that I am actually scaling this object down by half, 1:2. Okay. All right. So, this is the front view. So, I am going to mention that over here. Top view, mention that over there above the hinge line. Draw the projection lines. The length remains the same. Okay. This dimension over here would be about 32, 64 divided by 2. Okay, and I will finish this bounding box, and I will draw the vertical hinge line. Here I will be sketching my, or rather drawing, not sketching, drawing my right hand side view. Extend the projection lines. Okay, and I will draw the bounding box over here. So, this length is the same as this length, 32. This is about 31.5. It's pretty much like a square. It's a profile view. So, the side view is also called the profile view. Okay. So, my profile view, for instance. Okay, I should have also extended the lines from here, and I would have drawn the 45-degree line over here. I should have done that. Be very careful. I am bound to make a lot of mistakes. Okay, so let's start with the final version of the drawing. I'll see this edge from here to here. I'll see this vertical edge. I'll see the vertical edge over here. Okay, although this is like a semicircle, I'll see the corner of that, or the extreme of that. Okay, I'll see this horizontal edge from both sides, and then I'm going to draw a projector from this point over here up to the top, and on this projector would lie this edge. Likewise, on this vertical projector would lie this edge. Okay. Well, I'm actually going to be working on the right hand side view alongside. All right. So, this is the edge that I draw here, the second edge that I draw here. Okay. Then I would draw this edge. So, this is about 64, 38. So, 64 minus 38 is whatever dimension divided by 2. So, its dimension is given 13, 13 divided by 2 from both sides. I would draw this projector from here to here. Okay. Likewise, the other vertical projector. This dimension is 18, so I'll mark it 9. Note that I'm working with 1:2 scale. That dimension is 13 over 2, 6.5. This one is again 6.5. Okay. This is 13 from bottom from here, so it's about 6.5 from there. I'll draw this vertical edge down and this vertical edge down. Okay, and I will also see this edge right there. Am I done? Not quite. Would I be seeing this edge? Yeah, because this would actually correspond to this edge right there. Am I done? Again, not quite. How about these circular holes or cylindrical holes? I'll have to depict that as well. Now, if I look at this object from this side, are these holes visible? No, but they have to be shown somehow. So, I am going to show that using hidden lines or dashed lines. Okay. Nevertheless, I will work on them a little later. Let me project this guy here onto the right side view. I will start working with the top view. So, this is this edge that I have drawn there, this edge that I have drawn in my top view, this edge here, very easy. Okay, I draw the center portion, mark this as 19 divided by 2, which is 9.5, I guess. Draw this edge and dimension. So, always a nice idea to dimension while you are drawing different features of the objects in 3 different views. This is 9.5, 19 divided by 2, and then I will depict this edge and this edge, and then I will complete this loop. So, this part is very nicely visible in the top view. What else? Well, this edge, and then there's this edge, right? Okay, so I already know what this dimension is. So, from here I can measure what this extent is. All right, so these edges would also show up on the right side of the top view, and then I would mark the center. Okay, I would mark the center line, and then I will draw this semicircle on the left as well as on the right. Okay. Well, ideally, before I did that, I should have marked the vertical center line as well as the horizontal center line on both sides to, depict the center of the semicircle as well as the circle. Nevertheless, maybe I am not that patient enough. So, I do that now, and with these as centers, I draw a circle of diameter phi 22 on both sides. Okay, so this dimension is 114 divided by 2, 57. That dimension is 64 divided by 2, which is 32. Now, this is of radius 32, so I am going to be using a leader. Now, the way I depict this leader is as if I have an arrow, this line pointing towards the center of the semicircle at 45 degrees or 30 degrees or 60 degrees if you have many such circular features here. So, this one is at 45 degrees, and then I will draw horizontal, and then I will depict, this is R16 scale 1:2, okay, and that one again at 45 degrees on the other side of diameter 11 scale 1:2. So, since there are two circles, so it is like 2 times phi, that represents the diameter, times 11. Okay. Am I done with the top view? Not quite, or perhaps, I don't know, you tell me. Now, I should have dimensioned this before, but I am dimensioning it now. So, this is about 13 divided by 2, which is 6.5. Okay, so as I said before, there would be two circular features here also getting represented in the front view. So, I chose to first depict those circles in the top view and then project the corresponding feature onto the front view. So, I project the center line first on both sides, and then I project the endpoints of the diameter of the circle on both sides again. So, since the circle is hidden, it is going to be shown using hidden lines on both sides. So, this is how nicely these projectors they work. You do not have to measure things every time. So, the projectors they do that for you indirectly or implicitly. So, things become a lot more efficient. So, it's always a nice idea to keep drawing projectors alongside when you are working with the main drawing. Okay, now to the right side view of the profile view. I am now extending these projector lines, 45-degree line over here. So, from this side I am going to be seeing this edge, which is pretty much this edge. Okay, I will be seeing the edge corresponding to this surface, the verticals, the extent, extreme right and left, and I am going to be now seeing this edge right there and this edge right there, and then I am going to be seeing this edge right there. Now, like I did for the circles over here, I will do the same thing for the profile view. First, I will project the center line, draw the center line in the profile view, and then project the extremes of the circle onto the right side, and then again in the right side view or the profile view, the circle or the circular features are going to be hidden. I am going to be showing those features using hidden lines. Now, would these two lines cover only this circle or both circles? Question. Right, they will be covering both circles. Okay. What else? Now, this slope is something which would be explicitly visible only in the profile view, not in the front view nor in the top view. So, you would know the extreme point for this feature here, this location, which is at this height, and then you would also know the extreme point for the slope right there. Okay, right here. Okay, so this slope is going to be represented by a line, a slant line in the profile view. So, starting from here, ending up till here. There you go. Anything else that I may be missing? Well, let's see. As I said, are we missing this line or not? This line essentially corresponds to this line in the top view. Are we missing anything else? Perhaps not. But this example, I deliberately made 3 mistakes. I will talk about that, something that is quite common amongst you. So, you would do that. Mistake 1, I have depicted scaled dimensions, but not true dimensions. Now, what is going to happen? By convention, I should be depicting true dimensions. Okay? The reason is because I am mentioning the scale over here 1:2. So, of course, any person who is interpreting these drawings, he or she would know that the drawings themselves are scaled by half, but he or she would actually see the true dimensions if I depict them. Number 1. Number 2, look at these decimal points 9.5, 6.5, 6.5, 6.5, 31.5. It's not a good idea to show numbers by means of decimals in your drawing. Always a good idea to show your drawings by means of whole numbers. Mistake 1 that I made, you should not make those mistake or that mistake. Even if you are scaling your drawing, you should be depicting true dimensions. Mistake number 2, look at the way I have dimensioned the drawing. The larger dimensions, they happen to appear to be closer to the object, whereas the smaller dimensions, they happen to appear to be away from the object. Again, not a good idea. Should be the other way around. Smaller dimensions, they should be represented closer to the object, and larger dimensions, they should be represented away from the object. Mistake number 3, dimensions have been repeated. So, try to depict the information as concisely, as tersely as possible. Do not repeat dimensions. Okay. Now, if I do not make these mistakes, oh, by the way, I already told you about the leader. So, this would be an arrow which is at 45 degrees. Well, just emanating from the center, okay, at 45 degrees to the horizontal, and then there would be a horizontal line, and above that horizontal line, you are going to be mentioning the dimension. It's called a leader. Likewise, we have a leader here as well. Already mentioned that before. Okay. So, this scheme of dimensioning is called the aligned dimensioning. Look at the horizontal dimensions. We have an arrow with arrowheads on the right and on the left, and the dimensions happen to appear to be above the dimensioning arrow. For the vertical ones, imagine that you have rotated this thing 90 degrees clockwise, something like this. Okay. So, not only would the arrow get rotated, also the number would get rotated. So, the arrow, the vertical arrow would look like that, arrowheads on both sides, and the number is going to be aligned with the arrow. So, if you imagine that this is rotated by 90 degrees anti-clockwise, the number will be appearing on the left of the dimensioning arrow, aligned dimensioning. Okay. That is an example. As I mentioned, the number above the arrow for the horizontal dimensions, okay, and for the vertical dimensions, the number to the left of the arrow, okay, but aligned with the dimensioning arrow. So, you would not want to write 32 as this on the right side, or even 32 as, you know, being aligned to the horizontal line. That would not be correct. Okay. So, if I correct those mistakes, if I bring in smaller dimensions inside, the larger dimensions outside. Okay, but before that, in case of horizontal dimensioning, dimension or the number below the arrow is incorrect. In case of vertical dimensioning, dimension on the right hand side of the arrow is again incorrect. Mention that just to emphasize. So, if I go back, for instance, and if I try to correct these mistakes of mine, mistake 1, mistake 2 and mistake 3, and if I depict all true dimensions, number 1, number 2, if I depict smaller dimensions closer to the object, larger dimensions away from the object, and if I make sure that the dimensions do not get repeated. Okay, let me go forward. My drawing would pretty much look like that. Okay, smaller dimensions closer to the object, larger dimensions away from the object, all these dimensions in true scale. Okay, the fact that I mentioned the scale over here gives the interpreter feeling that these drawings are actually scaled by half. Okay. All right. And of course, I have let go of repeated dimensions. Okay. All right. So, first example in orthographic views. This is one of your lab problems. I'll end this lecture here. Keep thinking and analyzing until we meet next time.
Engineering drawings and blueprints are a type of graphical language that communicates ideas and information from the engineer who designed a part to the workers who will make it. The graphical images in the field of the drawing are generated using a variety of line styles. Acceptable quality and consistency of the lines used to create blueprints is critical to accurately depict the final product. The lines described herein are merely conventions. Each drawing specification may have its own types and standards. Visible lines, sometimes called object lines, represent the edges or lines on an object. They are solid lines with a thick weight. Hidden lines consist of short dashes, evenly spaced. These lines are used to show the hidden features of a part. They begin with a dash in contact with the line from which they begin, except when such a dash would form a continuation of a full line. Center lines are composed of long and short dashes, alternately and evenly spaced, with a long dash at each end. Very short center lines may be unbroken if there is no confusion with other lines. On a front view, center lines cross without voids. A center line can also make the center of a hole on a side view. Hidden lines are used to show the extent the hole reaches into the part. Section lines are used to indicate the exposed surfaces of an object in a sectional view. They are generally thin, full lines, but may vary with the kind of material shown in section. Section lines are typically used when showing details of a part, where using hidden lines would be confusing. Section lines illustrate where material would be if the part were sectioned or cut, as if with a saw. Different patterns or direction of lines indicate different sections of the object. Dimension lines typically terminate in arrowheads at each end and include the dimension of the part within the line. They are unbroken except where space is required for the dimension. Extension lines are used to indicate the extension of a surface or to point to a location outside the part outline. They start with a short, visible gap from the outline of the part and are usually perpendicular to their associated dimension lines. They help illustrate how far a dimension extends. Leader lines are used to indicate a part or portion to which a number, note, or other reference applies and are typically unbroken lines terminating in an arrowhead. The most common use is when a dimension won't fit within the dimension line. Cutting plane lines are used to indicate a plane or planes in which a section is taken. The arrows at the end of the cutting plane line indicate the direction of the view or the direction your eyes look after the cut is taken. A viewing plane line is a line that indicates a special type of detail view. A viewing plane line is very similar to a cutting plane line, but it does not actually cut the part or generate a section. A viewing plane line is used when an interior view of the part is helpful in illustrating characteristics, but a full section view is not required. Break lines are used when a portion of the piece shows no useful information, and removing it is either convenient to save space or will allow further details to be illustrated. There are two types of break lines. Long break lines are typically full ruled lines with freehand zigzags that are used to show breaks in shafts, rods, tubes, rope, and so on, which have a portion of their length broken out for convenience. Short breaks are indicated by solid freehand lines and are typically used to illustrate smaller section views where removing material from the part illustrates features otherwise not shown. Phantom lines are composed of alternating one long and two short dashes, evenly spaced, with a long dash at each end. They are used in three ways. The first is to indicate the alternate position of moving parts. The second way phantom lines are used is to illustrate the position of related parts to better show how the part interfaces with existing or missing parts. Finally, phantom lines are used to show repeated detail. In this view, a spring is depicted. Since the coils of the spring are all the same, it's not necessary to draw them all. Instead, phantom lines are used to illustrate that the coils continue as originally shown.